This project is a smart plant care system, an IoT system designed to monitor and take care of a plant automatically. Our proposal solved the problem of manual plant care by using a sensor for soil moisture, temperature, and humidity to water a plant automatically and send the alerts. Look at the system architecture. Raspberry Pi sensors sends the data through an MQTT broker to our analytics, catalog, and alert services. This data goes directly to Node-RED, Telegram, and a ThingSpeak cloud. Finally, in the VS Code, the repository is divided into a clear folder for each service, like Raspberry Pi, Analytics, Telegram bot, and a Node-RED, all running together using Docker Compose.
Mosquito serves as the central MQTT message broker for the system. Its primary job is to act as asynchronous publisher-subscriber messaging hub, decoupling edge sensors from analytics module alerts generators and cloud adapters. When a sensor publishes a message, Mosquito immediately distributes it to all subscribed microservices without requiring direct client-to-client connections. Let's look at Mosquito.conf, which control how the broker behaves. Line 1 tells Mosquito to enable persistent state storage. Instead of storing subscription and QoS messages strictly in RAM, it saves state metadata to disk. Line 2 defines the exact container directly where Mosquito writes its state file, MosquitoDB. Line 3 directs broker lag to a standard output. Line 6 disable mandatory username and password authentication during development, allowing our local microservices to connect seamlessly without hard-coded secrets. Line 8 binds the broker to listen on the network port 8083, the international TCP port for unencrypted MQTT communication. As you can see, in the left terminal, Mosquito subscriber is actively listening on topics. Our Raspberry Pi nodes are publishing live sensors every few seconds. You can see real-time updates for temperature, soil, moisture, humidity, and UTC timestamps streaming directly through Mosquito. In the right terminal, we execute Mosquito Publisher to target the topics directly with a consume JSON payloads. Because Mosquito handles asynchronous publisher-subscriber routing instantaneously, any message published on port 8083 immediately fans out to all subscribed consumers.
In our smart plant care system architecture, the Raspberry Pi Edge service acts as the main node for collecting sensor data and controlling plant devices. This service lives inside directory and run as a separate microservice. It sends the sensor data to broker, receive a control commands, and work independently from the central cloud server. This Docker file creates the container environment for Raspberry Pi sensor application. It starts from Python 3.11 Slim image, which is a lightweight version of Python that helps keep the container small and efficient. The working directory is set to /app, which is where the application file will be stored inside the container. It defines environment variable to configure the application. The Python variable improves how the program runs by preventing unnecessary bytecode files and making sure a log are displayed immediately. The device variable stores information about the sensor node, such as its ID, name, and type. The MQTT variable the communication with the MQTT broker, including the broker address, port, topic, for sending the sensor data and receiving comments. The Docker file also sets the connections to catalog services and define timing setting, such as how often the device publishes data and how often register itself after configuration is complete. It copies the requirement file and installs all the requirement Python libraries. Then it copies into the main application file into the container. Finally, the cmd command runs the main.py automatically when the container starts. The requirement.txt file contains the Python library needed for the sensor application to work. It includes a request, which is used to make a HTTP request, and also it includes the POW MQTT, which allows the device to communicate through the MQTT by sending the sensor data and receiving the comments from the MQTT to broker. The next file in the Raspberry Pi folder is a simulator.py. This file is responsible for simulating the physical environment of the plant sensor node. The main component in the file is plant simulator class, which generates realistic sensor value and handle control commands. At the beginning, the file imports several libraries. JSON is used to format the control save output. Mass is used for environment calculate, random, and small variable to make the sensor reading more realistic, and threading is used to handle safe access to shared data. The function now UTC is create a UTC interstamp in an ISO format. This timestamp is adding to the sensor data so each reading has a clear time reference. So after that, inside our plant simulator class, the constructor init initialized the simulator. It stored the device ID and created threading.lock. The lock is important because sensor update and commands can happen at the same time, so prevent the data conflict and keep the simulation state consistent. The simulator starts with an initial soil moisture value generated randomly between 25 and 90%. It also created temperature and humidity bias value, which are used later when the control command modified the environment. The control state dictionary stores the current actuator state, such as watering, temperature control, humidity control, and the information about latest commands. The diffraction function calculates the current time as a fraction of 24 hours. This allowed the simulate create a natural daily pattern such as high temperature during a day and low temperature at night. The update environment state function is responsible for changing the simulator environment over time. Soil moisture naturally decreases to represent water being consumed by the plant. However, if the watering command is active, the soil moisture can increase or decrease depending on the requested action. However, if the watering command is active, the soil moisture can increase or decrease depending on the request action. This function also updates temperature and humidity adjustment. For example, when cooling is active, the temperature gradually decreases. When heating is active, it increases. The same idea is used for humidity control too. The read temperature function generated temperature readings. It used a mathematical sign function to simulate daily temperature change and added a small random value to make the result more similar to a real sensor. The temperature is then limited to a realistic range. The read soil moisture function returned the current soil moisture value, which is a small random variable, simulated sensor noise. The read humidity function works in a similar way to the temperature. It creates a natural humidity pattern that changes throughout the day and also includes a small random variation. The collect data function is used to gather the latest sensor information before collecting data. It updates the environment state and then returns to a JSON object containing the device ID, temperature, soil moisture, humidity, and the timestamp. The handle comment function processes comments received from the MQTT broker. It checks the comment type and updates the internal control state, for example, increase watering. The handle comment function processes comments receiving from the MQTT broker. It checks the comment type and updates the internal control state, for example, increase watering, active watering, or start on line cooling, change the temperature control state, and increase humidity, adjust the humidity level. Finally, the print control state function displays the current simulated control state, including the active controls and information about the latest commands. Overall, these files act as a virtual plant sensor. It replaces a real hardware sensor by generating realistic data, responding to MQTT command, and providing the sensor readings that can be published to the rest of the smart plant system. This file is the main program of the Raspberry Pi sensor node. It's responsible for connecting the device to the Catalogue services, communicate through MQTT, collecting sensor data from the simulator, and publish the data to the rest of the system. At the beginning, the file imports the requirement libraries. JSON is used to encode and decode messages. OS is used to read configuration value from environment variable. Threading allows different tasks to run at the same time. And time is used for delay and timing operations. The request library is used for HTTP communication, which the Catalogue service, while pow.mqtt.client is used for MQTT communication. Finally, the plant simulator class is imported to generate the simulated sensor readings. The main component is the sensor node class. This class represents this Raspberry Pi device in the smart plant system. Inside the init function, the sensor node receives basic information, such as device ID, MQTT topic, broker address, and a port number. These values are stored so the node knows how to communicate with other services. The constructor also loads additional configuration from environment variable. Default values are provided in case these variables are not defined. After that, the code creates the MQTT topics dynamically. The sensor topic is created using the base sensor topic and the device ID, while the command topic is created using the command topic base. and the device ID, this allows each device to have its own communication channel. This simulator is responsible for generating temperature, humidity, and soil moisture data. The MQTT client also initialized and callback function are assigned for connecting, disconnecting, and income messages. The register device function handled registration with the catalog services. It created JSON payload containing the device information, including the ID, name, type, sensor topic, comment topic, and status. Then it sent an HTTP post request to the catalog services. If the registration is successful, the device is added to the catalog. If the device is already registered, the program detects this and continues without failing. If there is a connection error, the function returns false, so system can retry later. The registration task function run the registration process in a loop. If registration fails, it waits for a few seconds and tries again until the device is successfully registered. The next section contains the MQTT callback function. The onMQTT connect function is called when node read connection connects to MQTT broker. If the connection is successful, it subscribes to the comment topic, which quality of service level 2, meaning that comment messages are delivered reliable. The onMQTT disconnect function updates the connection state when the MQTT connection is lost. The onMQTT message function handle incoming MQTT comments. It read the message payload, convert it from the JSON format, and send the comment to the plant simulator using the handle comment function. This allows the simulated plant environment to react to comments like watering, heating, and cooling, or humidity control. The MQTT loop function maintains the MQTT connection. It continuously tries to connect to the broker and keep the connection active using a loop forever. If an error occurs, it waits and tries again. The publish loop function is responsible for sending a sensor data. When MQTT is connected, it collects the latest sensor readings from the simulator, convert the data into the JSON format, and publish it to the sensor topic. This message uses QoS level 2 to ensure reliable delivery. After publishing, the function waits for a configuration publishing interval before sending the next sensor update. The run function starts to complete the sensor node. It prints basic information about the device. Then created 3 separate threads. One thread handles the catalog registry, another manage the MQTT connection, and a third publish sensor data. The stop function safely shuts down the sensor nodes. It stops the running loop and disconnects from the MQTT broker. Finally, inside the main section, the program creates the sensor node object using a configuration value from environment variable such as device ID, MQTT topic, broker address, and a port. Then it starts the node by calling the run function. Overall, this file acts as the main controller of the Raspberry Pi sensor node. It connects the simulator with the catalog service and the MQTT network, receives comments, generates sensor reading, and publishing data to the smartplant system.
Catalogue is one of the main microservices in our smart plant care system. It acts as a central registry of our system. Instead of that, each service stores its own information. They communicate with just the catalog. The catalog also stores the user Raspberry Pi, registered microservices, and the global configuration of the project. As we can see, the catalog contains 4 important parts. First, we have a data folder that it contains the catalog.json. Here, this is the actual database of our project. Then we have the Docker file, main.py, and the requirements. Now I will explain you the catalog.json as a database. As we are not using the MongoDB in our project, all catalog information is stored inside this JSON file. Here it contains all information that's shared by the system. The first section is users, second is devices, and then services and config. In the users, we store a unique ID, name, devices, the role, and status. Also, for the devices, here we have the ID, name, and the type of the device, MQTT topic, the comment, status, and also the creator time and the last update. That allow that every service in the system to discover the devices. The third part is about the services. Here also we store the ID, name, type, endpoint, status, the created, and last update or the timestamp. For the services that we have, that we know each service periodically register itself with the catalog. And last part is the config. Here we have the project name, the MQTT broker, the port, and also the important part is the thresholds. Here we dedicate for each of them the min max threshold for the config section. And here these value are most important because the analytic part use this threshold to analyze our data. Then we have a Docker file. In this section, define that how the catalog container built. At first, we use the official Python version 3 slim image because it's smaller than the normal Python image and reduce our container size. Also, we define the working dictionary as an app, and it means that every following command is executed inside the dictionary. And I have two environment variable. The first one disable Python cache file, and the second enable immediate console. This make the container cleaner and easy to debugging. Next, we have the copy of the main py, and then create a data dictionary because this is where the catalog JSON file will be stored. And we expose the port so other microservices can access to the catalog, and CMD structure that start a service by executing this main Python. And at the end, we have the requirement that Docker read this file during the build process and install just the dependency. Now we are going to analyze the main part. The main file contains the complete implementation of Catalogue REST API, and it's responsible for reading and writing the Catalogue JSON file and handle the user, device, services, and configuration, respond to get, post, put, and delete, and also start a CherryPy web server. All of them are including the one class, Catalog Web Service. Before we import a CherryPy, as you know, is responsible for running the HTTP server and receive the request like get, post, put, and delete. We import JSON because the catalog data is stored in a JSON. And also we import OS that we use it because of the read the environment variable and also check the catalog exists or not. Also from the threading we use to create the rlog that we describe it, and from date time we import date time and time zone that to generate a timestamp in the UTC time. Here in the class at first, we have the class definition, the line that exposed true, that tell the CherryPy that this class is accessible through the HTTP request. And then we have the constructor, the init file def, and catalog file. Also, we use the threading rlog and self-create catalog file. We use rlog is it's like a normal log, but the same thread can acquire it more than once. And finally, this file that guarantee the catalog exists before the server started. Here we have in the file management, we create a catalog file that creates the default JSON file when it doesn't exist. And then this is the instruction that we use if it's not exist, the user, devices, services, and blah blah, also the threshold as we see before. Then the config part contains the project name, MQTT information, sampling interval, and sensor thresholds. As you know, we show it also in the config.json as we had it here. Yeah, it's the same. Also we have it. Then we have a load catalog.self. Here, as you see, this method read the complete catalog file. We use the R, it means the read, and JSON load convert the JSON content into a Python dictionary and also return it. The method that we used here as a OS error handle the file related to the problems, for example, if the file cannot be opened or something like that. Then we save the catalog. Here, write the complete catalog to the JSON file, receive the complete updated as a dictionary, and W here is open the same file in a write mode and write the updated data back to the disk. And every successful that the post, put, or delete operation, all of them call this method. The next one here, we have a helper methods. For example, for one of them, we have the time that returns the current UTC time after create a time zone. And then for the error part, this helper create consistent error response. And another one is the find by ID that search into a list of the dictionary. Item can be the user's list, or the devices list, or the services as we had. An item ID is the ID request that we had it in the client, the ID of the client, I mean. And it loops through every item that, for example, if item gets ID equal to this one, they get safely read the just the ID file. Next, we have a find position by ID. It's similar to before, but similar to the previous one, but it returns the index of the item instead of the just object. And the enumerate here give both the position and also the item file. The next one, we had a validation user. We validate all of them, user, devices, and services. For example, in the user, check whether a user, for example, contain all the required field or not, the name, device, and the Telegram ID. For example, if a field, one of them is missing, it returns an error for us. The next one is the validated devices and also the services. All of them check both whether the field exists and whether it's empty or not. And then for the validated services, here is the same for all of the microservices, and the required field are ID, name, type, and endpoint. As you know, for example, Analytic must provide its service ID and endpoint before the register. Also, we have this for the alert generator or the other microservices. Then we have a check catalog. Here, the method prepares the catalog before processing a request. First, one, it tries to load the file, and if loading fail, it returns, for example, the value, the error response. Also, status is 500 because this is a server-side storage problem. And in a set default, as we have, it means if the key already exists, keep the value, or for example, if the key is missing, create it with the default value. Here in the get, this pattern used for all REST method, the decorator JSON out tell cherrypie to convert the written Python dictionary into the JSON. We have a star URI that store the URL path. For example, if get devices we had, it produce the URI devices. And also we have the params that has store the query parameters that we can see more. Here, if the len is larger than 2, we had the error that describe this part. If the Telegram ID here also is in param, here we return it. If not, we have a error for 100. Also, for the len URI is equal to, we have this description, and also the error is occur with 404 here. This is also the same just for the devices, and also we have it for the services as the same. All of them, as you know, used by the ID. Also, we had the config here that this endpoint only accept exactly the one pass. So here the config /test rejected, and on the return self error response here, if no resource matches, there is another error 404. Then we go to the post part here. As we define a cherrypie, also is the same. The cherrypie tells it to parse the request body as a JSON. And the post only accept the collection endpoint if there is a, for example, user devices or the services. Then if not is instance new item, the body must be a JSON object, not a list or, for example, a text. On the post users, the user object is validated first, and if the method return a message, the requested reject with for 100 again. And then The code also here check the duplicate IDs. If it's not, return the 409. Then we had a set default as we had it before. Then the new user is append to the list and then save it. If it's successful, we had a 201, and if not, there is an error. Also for the post devices, it is similar as before, and after the validation and duplicate checking, the timestamp generated. Then we have post services here, that the service registration is one of the most important because it's idempotent. That we mean that the repeating the same registration doesn't mean analytic folder contains 4 main files: the config.json, docker, main, and the requirements. The config.json contains the MQTT topic and command names that used by the service. And in the Docker file, define how the analytic Docker image created, and also the requirement just mention the libraries that we needed, and also at the end the main part is the main that complete implementation of analytic service is inside this one. At first we start with the config.json. This file contains the local configuration that we used, and it's separate from the catalog configuration. And the important difference is that the catalog stored a dynamic system value like a threshold, while this local file stored a fixed MQTT topic name and the comment. Here the first part, the sensor topic, is define the topic that analytics subscribe to. Here the hash is the wildcard that we used, and it means that the analytics service subscribe to sensor data from all the Raspberry Pi devices that we have. And also here we have the comments. Then for the Docker file, as I said in the catalog, here we use the a slim version because this make the Docker image smaller. The workdir app creates this and select the app as the working dictionary inside the container, and 2 environment variable. The first one stop the Python from creating the extra cache file, and the second variable make the Python log appears immediately. We copy the requirement or the libraries that we need and run pip install, install every required Python package that we need. Again, here we have a copy of the main and config. Here in the main we have the service logic, and in config we have the local MQTT and command. This is the expose port, and at the end the final instruction start the analytics service by executing the main Python. And in the requirement also we have the cherry pie request and power MQTT, the library that we have to install and contain it. Now I explain the main file of the analytics services. This service is different from the catalog because here also we have the MQTT and HTTP. The catalog mainly provide a REST API and store the data, but the analytic here serve also connect to the MQTT broker, the receiver sensor data, and also apply the rules, publish command, and send the analysis result to the alert generator. Here, all of this logic are in the class analytic control service. We expose true because true allow cherry pie to expose this class through the web server. And the one important thing is the sensor rule that inside it we store the command, and we dedicate it with low, high, normal for each humidity, soil moisture, and temperature. Then we have the main part, the init, that the constructor prepared the entire analytics services with self ID, name, type, host, and port, identify the service, and define the host port that's used for the cherry pie. For the self catalog URL and registration and the threshold, each one is responsible for one thing. For example, the catalog store the internal address, the rstrip method remove a final slash, and the registration retry used when the communication with the catalog is failed, and the threshold refresh define how often analytic reload this threshold. The MQTT here that we have, this value define the mosquito broker, the port, and the location of the configuration file. We have with open that we read the config.json and store the content in the self config. The file contains the MQTT topic and command value used by the services. Then we validate it. After loading the file, we validate it immediately. And the self log also we used the same in the catalog. The rlog that they may read or update the same data in the same time, and rlog protect this data. The self latest data here store the latest sensor payload received from every device, device ID used as the dictionary key. Here we have two lists, store recent command and recent analysis result. They are used by the also REST API, and the dictionary that store the last command sent for every device and sensor. Then we have a threshold, store the current threshold value that we download from the catalog. At first we consider it's none. The threshold already is a here is a thread event, and it is set after the threshold are successfully loaded. For the MQTT client, this boolean store the current MQTT connection state. Then here this create the PAHO MQTT client as we learned, and the clean session mean the broker doesn't keep an old persistent session after the client disconnected. We have on connect, disconnect, and on message that connect the MQTT event to the class. Here we go to the now UTC is ISO that this method return the current UTC time. After we have a sensor topic that return the sensor subscription topic from the local configuration. In the command, build the command topic for just one device, and in the analysis, this use the same approach for the analysis topic, and it's based on the config.json and the device ID. We load the configuration validation here. We used the MQTT config and we validated here it means this is an internal herpel method, the MQTT and command we use get with an empty dictionary as a default. Then we have a require MQTT. This tuple contains all MQTT configuration key required by the services, and in the missing, this list comprehension collect any missing or the empty MQTT value. If the list is not empty, the code raise a error. We have a require command. Instead of writing every command key again, the code read them from the sensor rule, and this prevent to duplicate configuration. If missing command, this check that every command key exists in the command section. If one of them missing, then we have another error. In the catalog communication, we have a registration payload that here the method build the JSON used to register the analytic in the catalog. And as we can see, it has the ID, name type, endpoint, and the status. This is the endpoint. The registration service, this method send the registration payload also to the catalog. We have a request.post that it use HTTP post request, and the payload is passed using the JSON parameter. The timeout prevents the thread from the waiting forever, so we used 221. That both of them is accepted. 201 means a few service registration created, and 200 means an existing registration was refreshed. Then we have this accept request that this catch HTTP connection error and other, for example, problems. The registration task here define here with the registration task that this is a continuous task. It register or refresh this analytic every 60 seconds. This is the loop, and the extract threshold. This one, this method validate and normalize the threshold data received from the catalog, and first it check it that it's in the is a JSON object represent as a Python dictionary, then support both a direct configuration response and a response wrap inside the config key. Then we have a here we have a validate that this method loop through the same supported sensor defined in the sensor rule. This keep the sensor list consistent across the service. We have a limit that it read the minimum and the maximum value for the current sensor that we have, and the value are convert also to the float. And if, for example, the mean is larger than the max, check the validity of the range. Then we have a load threshold from catalog here. As you can see, this method download the current configuration from the catalog, and if it's send a get request to the configuration endpoint, then response raise for a status that this raise an exception for unsuccessful HTTP status code. Also here we have a new threshold set that threshold from catalog here. We download the current configuration from the catalog, and then send a get request to configuration endpoint. This raises an exception for unsuccessful HTTP status code, and the JSON response is passed to the validation method. Here we self-lock the threshold update and related shared data access and protect by the lock. Then here this is detect whether the new value are different from the current value. We have this cell that the new threshold store and the update time is refreshed. The snapshot create a copy of the latest sensor data. Then we say that if changed, if the threshold changed, the service evaluate the latest sensor data again for us. If the threshold are unchanged, the method only log a successful refresh, or the exception block handle the errors, HTTP error. Then we have a threshold refresh task here that this is another continuous task. We try to load the threshold, and if loading succeeds, the normal refresh interval, we use it. But if it fails, we have the shorter retry delay, use it. The get threshold snapshot here with self-log. This method return a safe copy of the current threshold, and the log protect the read operation. We have an MQTT unconnect, disconnect, and on message. For the connect part, also this method called automatically after MQTT connection attempt is 0, return code 0, mean the connection succeed. And the other ones, here the QoS is 1, we consider. If the connection failed, the state remain false, and the return code also printed. For the on-MQTT disconnect, this callback run when the MQTT connection, for example, lost, and it depends to the MQTT to false and logs the return code. For the on-MQTT message, this is the main MQTT input method. It's run whenever the sensor message arrives here. The MQTT payload arrives as a byte, and first it is decoded into text, and then the JSON text is converted into a Python dictionary. The device ID also is required because it identifies the sender and is used as a key for us. Here, two internal field we have. One store the actual MQTT topic, and the received at. This is the another one that store the analytic receive time. With self-log, the latest payload for that device is stored very safely, and after storage, the payload is sent to the rule engine for us, and the error handled the invalid JSON. The MQTT loop here method maintains the MQTT connection in a continuous loop. It connects to be configured the broker, and the keep live value allow the client and broker to detect connection. Here we have the start the PAHO network loop, and the network loop receive message and execute the MQTT callback. After that, with publish JSON, this is a command publish helper used by both command analysis message. First, it checks the connection state. If MQTT is disconnected, the method doesn't attempt to publish. And for the if the Python dictionary converts also into JSON text and publish with QoS 1, then the method check the PAHO return code and return a Boolean result for us. After that, we have a publish analysis here. This method for us publish the result of a rule engine, and it builds the device-specific analysis topic. The history is updated whenly. The MQTT publish request accepted. Then we also append this to the history, and there is also the limit to the latest 500 item to prevent the unlimited memory. We have a publish command here that the method publish a command to one Raspberry Pi, and with self-log here, this read the last command sent for the same device and the same sensor. If the new command is identical, the method is stop. And this is the avoid sending the same command for the same device. Then we mentioned the payload here. The payload contained the target device, the related sensor, and the command and the timestamp. After successful publishing, the command is appended to the history here, and the history is limited also to the 200 items. The set default creates also the dictionary for the device if it doesn't already existed. And then in the main parts of the rule engine, at first we evaluate a sensor, that this is the main decision. It evaluates one sensor value for one device. If the sensor is missing, the method is skip it, and the raw value is converted to float also, and invalid numeric data is locked. We consider min-max, the current limits are read from the validated catalog threshold, and for example, if the value is less than the threshold mean, is low, and the other one for the high and normal. The command selection code combine the selected state with the sensor rule definition to find the correct command key, and also the final command value is then load from the config JSON. The analysis here, the payload, the object contain the complete result of the decision, and we consider this one for it. Then here for the evaluate control, this method evaluate the complete sensor payload, and it first retrieve a safe copy of current threshold. If threshold, for example, is known are not ready, the service skip it. This prevent the decision based on the missing configuration. But if the device ID read, the method loop through all the supported sensors. And the same evaluate sensor method is repeat for the temperature and the soil moisture and the humidity. In the catalog and live telemetry merge, at first we have a fetch catalog that this method retrieve registered device from the catalog, request that get, send a get request and check the status. If the catalog is unavailable, we have the error 503. And the error about the JSON, invalid JSON, we have a 502. Then we have a normalization, and if the response itself is a list, it's used directly. But if the response is a dictionary, the code first look for a device key here. Then if not here, if normalization doesn't produce a list, the method, for example, we have a error 502, and the final list compression return only valid dictionary item contain a device ID for us. Here for the merge registration devices, this method combines the two sources, the registered device information from the catalog and the live sensor information that is stored by analytic. It loads the official device registry, and then with self-flag, then it creates a safe copy of the current telemetry. Here we use a merge. The final result is stored as a dictionary by device ID. For catalog device, the method loop through every registered device, and it supports either ID field name and this loop for the latest sensor payload from the same devices. And also we have all of the MQTT topic, latest data, the telemetry, and all of them. And for device ID, latest here, this second loop handle the device that have published sensor data but are not registered in a catalog. The repeated structure keep the REST response consistent for all of the devices. Here in the REST API, at first we have this cherrypy JSON out that convert Python object into the JSON, and the path that contain the URL segments. Here, if not pass, if the path is empty, the method return the service message and the list of the available endpoints. These are the endpoints that we have. And the first path segment here, select the requested endpoint. If resource is the health, these endpoints report the current, for example, service state. And also we have it for other one, the ID, MQTT connection, the threshold, and blah, blah. For here, the device endpoint, if, for example, is devices, we use the match register devices, and for here, if it's equal to 2, when a device ID is present, the method return only the device ID. But if it's not, we have a error 404. Also for the if resource is equal to the comments, the endpoint return the comment history. And also if, for example, the analysis, the endpoint return the analysis history. Then if here is equal to 2, when a device is provided, the code filter the history for us. And in this part, the list compression keep only the result from the requested device. And if it's not, the method raise the error 404. And for the rule, the endpoint return the current decision configuration, that it include the active threshold snapshot and the others. Also in the summary, we have the endpoint provide a compact overview of the service. It loads the merged devices and also the safely reads the history counts. After that, we have the raise cherrypy error here. That if no resource matches, cherrypy return F404. In the start thread, this method start, we consider 3 thread, the registration, the threshold, and the MQTT loop. For the registration, periodically register analytic in the catalog, and for the threshold, this thread periodically reload the threshold, and also for the MQTT, this thread maintain the MQTT connection and the network loop. Here for the stop, disconnect the MQTT client when the service is stopping, and for the execution block, as we learned, the block run when the file is executed directly, and the service object created. This run all of the load configuration, validated, and prepared the MQTT client for us. Also at the end, we have the service start. This is start threads, and here we have a cherrypy setup. Use method dispatcher, as we learned, that map the HTTP GET request to the class GET method. And at the end, session are also enabled in the configuration. This set the REST server host port and terminal logging. This connect the cherrypy shutdown event on the service stop method. And at the end, we have a start and block for the cherrypy that start the cherrypy engine, and the second one keep the process running. That was the whole part of the main for analytic.
The alert generator service has a hybrid role in the system. It works as a both REST API and MQTT event process. First, it processes MQTT message. It subscribes the live sensor data and also listen to analysis requests. Its main function is generating alert when the sensor value go outside the definition thresholds, such as temperature or soil moisture. It creates an alert and publishes it to its topic. Like the other microservice, the alert generator uses the same Python version-based image, the same project structure, and the same basic environment configuration for Python, the Catalogue service, and MQTT communication. This service also defines 2 additional environment variables. The first is a ThingSpeak Adapter URL, which allows the service to retrieve the historical sensor data. The second is a config file, which point is to config.json file. This file stores service configuration, define the MQTT topic that alert generator use to subscribe all sensor data using a wildcard to listen, analyze, and request, and publish an alert using this topic. It is specific to analyze report should also retrieve the last 20 sensor reading by default. Finally, Docker file install that required dependency copies the application file and expose port 8091 and start the service by running the main.py.
The requirement.txt file contains the three main Python dependencies used by the alert generator service. CherryPy is used to create a REST API web server, request allow communication with other services through HTTP call, and PyMQTT is used for MQTT communication, including receiving sensor data and publishing the alert or comments. The main.py file contains the main logic of an alert generator service. At the beginning, the file imports the requirement libraries. An IUTC is a function is used to get the current UTC time and convert it into an ISO format string. It removes the microsecond to keep a timestamp clean. This function is used whenever the service needs to record a time when the data are received or when the alert is generated. The alert generator service class contains the main logic of the application. It manages MQTT communication, service registry, alert generation, device information, report generation, and REST API operations. The init function is constructor of the service and run when the alert generator starts. It initializes all the requirement config. It also loads additional setting for environment variable, and also it will load the configuration file and create a storage variable like latest data for saving the newest sensor information, and alerts for storing generate alerts. Finally, it creates MQTT client and assign the callback function to handle MQTT connection, disconnection, and incoming message. The average function is help function to calculate the average of the list of value. It's later used when generating historical reports. The register service function registered the alert generator with a resource catalog. It created JSON payload containing the service information and sent it to the catalog using the HTTP post request. If the register succeeds, the service is ready to be discovered by other microservices. The registration task function runs in the background. If the registration fails, it waits for a few seconds and keeps retrying until the register succeeds. When the service connects to the MQTT broker, the MQTT connect function subscribes to both the sensor telemetry topic and analysis topic. This allows the service to receive a live sensor reading as well as analysis result. The MQTT disconnect function simply updates the connection state when the MQTT connection is lost. Every MQTT message is handled by an MQTT message. It first converts the received payload from the JSON into the Python object, then it checks the topic to determine whether the message contains sensor data or analytics result. Based on that topic, it's called either process sensor message or process analysis message. In the process sensor message function, we process a live sensor telemetry. It extracts the device ID, store the latest sensor value together with the MQTT topic at the timestamp, and update the internal state so the most recent data is always available. In the process analysis message function, we process analysis result. It checks whether the sensor value is outside the configuration threshold. If the state is either low or high, it creates an alert containing the device ID, sensor type threshold, current value, and the timestamp. Finally, it's called publish alert to send alert. The MQTT loop function keeps the MQTT function alive. If the connection is interrupted, it automatically waits a few seconds and reconnects to the browser. The publish alert function publishes the generated alert on the MQTT broker using the device's alert topic. It also stores the alert locally so it can later be accessed through the REST API. The fetch catalog device function retrieves the list of registered devices from the resource catalog using a GET request. The merge device function combines the registered device information from the catalog with the latest sensor data received through MQTT. This gives client both the device metadata and a current sensor value in the single response. The generate report function creates a historical report. It requests historical sensor data from the ThingSpeak Adapter, extract the temperature, soil moisture, and humidity value, calculate their average, and return the report together with the latest sensor readings. The get function implements all REST API endpoints using CherryPy. It provides endpoint for checking the service health list registered devices, retrieving a specific device, view active alert, and generating historical reports. The start function launched two background threads. One continuously registers the service with the catalog, while other maintains the MQTT connection. The stop function safely disconnects the service from the MQTT broker when application shut down. Finally, in the main section, the service is created using an environment variable defined in the Docker file. The background threads are started. The CherryPy server is configured and listen to the port 8091, and the service begin handling both MQTT message and the REST API request.
This service acts as the automated bridge between our local MQTT telemetry network and public ThingSpeak Cloud platform. It converts asynchronous event-driven MQTT payload into rate complaint HTTP REST requests for cloud visualization and historical storage. We start with configuration file. This file holds local environment parameters such as the local catalog service URL, MQTT broker, connection details, and default upload intervals. Next, requirements.txt specifies the external Python libraries required for these microservices. The Docker file containerizes this service. It uses Python 3.11 Slim-based image setup. The app working directory install dependency from requirements.txt, copies our source files, and executes main.py on container startup. Finally, main.py contains the core business logic. The service starts with two foundational utility classes. AppConfig handles system runtime setup by pulling environment variables for network endpoints such as our central catalog URL and MQTT broker, and provides safe JSON persistence helper for persistent storage. Shared state. Manage state across concurrent threads because these services simultaneously handles background MQTT loops, periodic catalog registrations, and incoming HTTP REST requests. Share states use a Python threading log to prevent race condition when reading or updating the latest message payloads, upload states, and local channel registries. Let's examine how these services dynamically integrates with the broader system ecosystem. Catalog service registration. In registration loop, daemon threads periodically sends an HTTP post request to our central catalog services. This advertises the adapter's health port and endpoint, keeping the system services registry updated without hard-coded infrastructure dependency. Automated cloud channel creation. One of the key highlights of code is zero-touch provisioning. When telemetry arrives from a brand new sensor node, the adapter executes ensure channel devices. If no channel exists in the local registry, it issues an HTTP request to ThingSpeak's API using our user key. It dynamically maps field 1 to temperature, field 2 to soil moisture, and field 3 to humidity. Extract newly generated write API key and read API key and saves them to channel underline registry.json for future update. Let's look at real-time message handling. Establishing a TCP socket connection with Mosquito port 8083, the client subscribes to the telemetry wildcard topic configured in config.json. MQTT loop runs on dedicated thread with automated 5-second retry to ensure resilience against broker dropouts. Payload enrich. When a raw bytes payload arrives from Mosquito, OnMessage dedicates the JSON data and enriches it with internal metadata including MQTT topics and ISO formatted UTC arrival timestamp. Payload mapping. Process sensor data, extract device ID, fetch its assigned write API key, and maps the incoming sensor keys to ThingSpeak's field. It then issues an HTTP post request to receiving an HTTP 200 success responses. It records the upload status in shared state and print confirmation logs. In addition to background MQTT processing, this microservices expose its own embedded HTTP REST API powered by CherryPy. Health API expose real-time diagnostic telemetry, returning the latest received MQTT message, payload, and the last cloud upload status timestamp. Registry API returns the current mapping of device IDs to their corresponding ThingSpeak channel IDs and API keys. History API acts as a proxy to fetch historical cloud feeds directly from ThingSpeak REST API for request device ID and result count, allowing internal dashboard consumers like Node-RED to query historical cloud data without needing direct access to external credentials. Finally, the entry point launches the MQTT listener and catalog registration loop concurrently before firing up CherryPy HTTP web server on port 8080. Now, let me walk you through our live ThingSpeak Cloud dashboard. On the main My Channel page, you can see 4 distinct channels. Each channel corresponds directly to one of our edge devices nodes. These channels were automatically registered via the REST API without any manual dashboard setup. Notice the updated columns sharing live ongoing synchronization timestamp as telemetry flows inform our Mosquito MQTT broker. Let's go to Raspberry 1 to inspect the live data stream. Here in the channel, view ThingSpeak render real-time time series charts correspond to the field mapped by our adapter. Field 1, track ambient temperature in degrees Celsius. Field 2, display root zone soil moisture percentage. Field 3, monitors relative air humidity percentage. Every time our simulated Raspberry Pi node publishes an MQTT packet to Raspberry 1, our ThingSpeak adapter parses the JSON structures, the parameters, and posts them to ThingSpeak, plotting a new data point live on these graphs. Under the API key tabs, we find the credentials that secure our cloud channel. Write API key used exclusively by our microservices to authenticate HTTP post requests when publishing telemetry. Read API keys allow internal applications such as our Raspberry Pi history endpoint or Node-RED dashboard to retrieve historical feeds securely without exposing administrative access.
Telegram bot is an automatic program that runs inside the Telegram messaging app. It can receive messages, respond to commands, send notifications, and interact with users or other systems without human involvement. For some common useful alerts, personal email support, data reporting, remote control, and integrating external services into Telegram chats. Now I'd like to explain the Telegram bot part. Let me start by explaining the overall structure of the file. The main.p1 is the most important part. It's a core part of the Telegram bot. The first part, we import all the necessary modules. Then I create a Telegram Plant class. This class contains all the methods needed to initialize the bot and manage all the other things. At first, we use the init. Job is to initialize everything in the bot and load the runtime configuration with file, verify the Telegram bot token exists, create the Telegram bot object, create the MQTT file, and register the message. Telegram bot token store in the environment file and the load JSON we use at the copy initialization and we read the copy file. I use this method copy file in the Telegram bot this now command and message and in the message load runtime copy the configuration file for environment file and paste them into dictionary. They are all include the key and the URL. The message NSG method read a specific message about the configuration message. This and the method safeguard JSON is important. The standard HTTP GET request to get keyword and get the response JSON file and turn into Python dictionary. Now let's focus on the user management. First is get alert generated. It is one of the most important parts, especially used for service discovery. Instead of depend only on the hard code URL in this. We ask the catalog service for available service and look for a service type is alert generator and the default is and the endpoint is our URL. And we use this URL instead of the default. And we cannot find this fallback, we return the default. Add to the log. And we have found the service which is called alert generator. Then the method get catalog users. Find the user in catalog by matching the table line. And get authorized user return the authorized user, which the status active. Get user device will return a device list. As authorized user ID, will check whether Telegram user is active or not. The method is defined allow for user check whether a given device can be selected by a specific user. Now returning into the service registration. Method register service and a host message payload about information to register the Telegram bot and service. I will do that. The registration loop, it will be run in the background, continuing when the service starts, and check about the service using the Telegram bot service. Then after that, method to get device map, and we can get a device list from the catalog and change the dictionary. And get allowed device map. We can get the allowed device by different IDs. This different user will be assigned by different devices. Get a device data. Curate the alert generator service to get a real-time status of the device. The command topic method is the MQTT topic used to send commands. This part is about MQTT, and this is MQTT loop. It will be another thread that run on the background to keep the MQTT service. Okay. Method publish command used to send a control message device over MQTT. Title and the topic. The format alert message define the alert message format with this, and it will be used for the form alert message. Send alert message. The alert action keyboard. If there is a reached alert, and there can be used for operation. If the temperature alert will start cooling, meaning the humidity is notify the user for alert method, send an alert to authorize the users and text the relevant part. If your former device status is the format of alert. This is the format report. This is the main menu keyboard, and it will show all the functions. The button that will be used. Click, device alert, need to report commands and devices, and will be returned about the message within this format. Device keyboard for user create a list of buttons for each device the user wants to access. Common action keyboard, the control button to send a command to device. Yes, control buttons. Method register handler attach Telegram handlers for chat message and callback queries. Method require authorization message, check whether users authorized for handling normal message. Method require authorization callback perform the same check for button click. The important part is the on-chat message and receiving context message and rows them according to the command. Command, different command will correspond to different handle method. Start, help, the device, status, alert, report. And if there's no message like this, it will be unknown. Finally, the method on callback query handle button press for Telegram is the place where the bot responds to main action, such as returning to the main menu, opening the device list, an alert, and so on. Send a command to the device. And then the run method can run the two thread and the background with an open MQTT tool. And this is the main function. Create a Telegram bot, send, and run. Let me show how to operate on the Telegram bot. This is a Telegram bot and start and show welcome to smartplant transition bot. Choose the action below. There are four things. As you can see, there is a device. I have a content control and this is other. No alert available. These are the report and these are the reports for 2. This is for 1. And press that. And then command run and do some operation about the device and particular device please. And also I can help and there are some instructions. Now I change my account. Change to another account. Look, there's another account. And I do the same thing again and prepare the device. They are different from the previous account. That's 3 and 4. Yeah, no alert available. And I can take the report. And go back. Now let's wait for the alert happen and what. Now there's alert happen. And see the alert message. High, low soil moisture. The value is lower than 0. So what we want to do is to increase the workload. Okay, let's go back. Let's go back and see the alert. Look, there's alert record. There's alert happen. Note that is a wisdom program to design or write together component devices. Device and online single flow based mode. Uses flows on the browser space effort to create automatically workflow without writing. In our project, we use for dashboard for remote monitoring and control. Focus on the notepad part. This is the notepad part of the flow.json. The other files store important information and the flow.json store the flow. The whole flow that is spread by these two parts, the gauge and the plot. Let's first talk about the gauge. The gauge requests per 5 seconds. The HTTP request get and return the JSON. And then we use the distribution that deal with the data and charge the alert by using this threshold. After that, we can get temperature, soil moisture, and humidity, and show with the gauge by this threshold, and then we collect all the alerts by this function and show them on this by using CSS. Look at this, it is alert, and we show like red instead of the default blue. Then we do the plot, the historical plot, request per minute. 1 minute. And we do see get, and then we deal with the data, and not the same as before, but we need to deal with more than one data. The data from last 1 minute, get a list and update the pod every minute. Then let's focus on the dashboard. There are 4 devices on the sidebar. We can choose one of them, and then you can see the left. There is a real-time method, down, and the temperature, the thermometer, and humidity. Let's see the color. The yellow shows that the temperature is a bit low. Thermometer and humidity, they are green, which means that they are in the right zone. And the right side, the historical chart, it shows the temperature, thermometer, humidity, the historical, because the node on the plot, every 20 minutes there's a point, and we update the plot every minute. Look, change its color, changing to red, which means that there is something in alert. So which one is alert? So the story motion in the recipe is lower than the threshold. So we can do some operation. We can use the Telegram bot.
While each microservice in our platform operates independently, Docker Compose serves as our multi-container orchestra. It standardizes container builds, configure isolated bridge networking, inject runtime environment variables, handle persistent storage volumes, and enforce short-order dependency. In total, this file defines 11 distinct microservices that are spinning up our complete IoT platform with a single command, Docker Compose up-d. I begin with core infrastructure foundation services. This is our REST-based system of record. It binds host port and uses persistent volume mounting to preserve system metadata in catalog.json across container restart. MQTT built from the official Eclipse.Mosquito image on Docker Hub. Mosquito handles our real-time publisher-subscriber messages backbone on runtime logs directly into the container. Now, let's dive into ThingSpeak Adapter, cloud sync engine that bridges Mosquito data to external dashboard. Analytics. Expose REST port 88 analytics. Expose REST port 8090 and subscribes to telemetry to compute statistical aggregates and system health metrics. Alert generator. Runs on port 8091. Notice it depends on list. It requires Catalogue, Mosquito, and ThingSpeak Adapter to ensure all reporting channels are active before evaluating threshold violation. Telegram bot acts as our interactive notification client. Telegram bot token securely injects secrets from a local.in file without hard-coding credentials into source control. It links directly to the internal container DNS, allows analytics, and alert generate. Next, let's look at how we emulate physical hardware nodes. Notice services Raspberry Pi 1, Raspberry Pi 2, Raspberry Pi 3. There are 3 architectural best practices implemented across this file that worth to highlighting. Embedded DNS networking. Microservices communicate using natural container names, for example, catalog URL and MQTT broker. Docker automatically resolves this name across the isolated bridge network, avoiding static IP management. Dependency tree prevents race condition during a startup by ensuring core broker and database initialize before worker services launch. Fault tolerance. Apply to every container, ensuring that if a service crashes or host rebooted, Docker Desktop automatically restarted the services. To wrap up our Docker Compose demonstration, I run Docker Compose PS in terminal. As shown here, all 11 containers from Catalogue and Mosquito to our 4-edge node and Telegram bot are running with a state-up and healthy port bindings. These confirm our entire microservice mesh is fully orchestrated and functioning in unison.
Now that we've walked through the theoretical architecture and detailed each microservice, let's see the smartplant care system in action. Now let's launch the entire system with a single command. Docker Compose spins up all our isolated microservices. As you can see from Docker Compose PS, all 9 containerized services are up and healthy. The Catalog microservice acts as our central registry. Here on port 8000, we can see all registered devices, services, users, and configurations. Mosquito runs a lightweight MQTT broker on port 1883, handle all pop-stop message routing between sensor nodes and the backend services. Every 10 seconds, our sensor nodes publish live temperature, humidity, and soil moisture telemetry to the Mosquito MQTT broker. Analytics is our data processing engine. As you can see on port 1890 and a Docker log, it continuously calculates moving average and evaluates the sensor stream against plant threshold. Alert Generator creates alert and reports. On endpoint 1891 alerts, you can see the recently alert events, and on a report, it generated plant health report with the average readings. Node-RED is a visual dashboard at the port 1880, show the live information and the graphs and the control toggles. Telegram bot is our mobile app interface. It sends an instant push alert, handle a comment, and let user through their manual comments, and also we have access for reports for each devices. And ThingSpeak Adapter push all telemetry to the cloud for a long-term storage and visualization. And that's how our complete system runs live. Thanks for watching.